Hello students, in today's lecture we are going to talk about the temperature stresses. Very often in the engineering field we encounter the machine components which are subjected to the variation of the temperature. This is very common. So there are usual rise of temperature and fall of temperature due to the weather conditions, and in some cases those temperature variations are due to certain machining process or maybe some other processes which are being carried out due to like some chemical reactions in other places. So whenever there is a change in the temperature, the materials which are subjected to these temperature changes are either expanding because of the rise of temperature or are contracting because of the fall in temperature. So in all these situations, if the materials are free to expand or contract, there will not be any stresses produced. Like if we take this first example, here there is a bar which is free to expand. On one side is attached to the wall, the other side of the bar is free. So when there is a change in temperature of, let's say, the T degree Celsius, so it will cause the expansion of this bar of the magnitude delta L, which can be calculated with the help of coefficient of expansion as L into alpha into T. L is the length of the bar, alpha is the coefficient of thermal expansion, and T is the change in the temperature. So this delta L will occur because of the rise in or temperature by T degree Celsius. Now, in case if the bar is not free while it is being contained between the two walls, so these retaining walls are not allowing any expansion or contraction of the bar, as here in this case 2, we will see if the temperature get increased, the bar will try to expand while the walls are restraining it or holding it down and causing the strain in this bar of the magnitude delta L by L. From the equation 1 we know the value of delta L, which we substitute here, and we can calculate it, the strain value, as alpha into T. There will be a corresponding stress caused because of this strain induced in this bar, and its magnitude from the Hooke's law we know is stress is proportional to strain. So using that we can calculate sigma, or the corresponding stress in this bar, of E times of alpha into T. The strain that is produced and the corresponding stress, they both are of compressive nature, because we are retaining this bar and not allowing the expansion of this bar will cause the compressive stress being induced. The reverse of it will happen if we reduce the temperature. So in that case the bar will try to contract and the wall will not allow it to contract, causing the tensile stresses of the magnitude, which can be calculated from equation 2 and 3 in this bar. Now if these walls which are holding this bar down are not perfectly rigid and they can yield by an amount delta, then in that case the deformation that take place in this bar will be the deformation given by equation 1 minus by the amount the wall has yielded. So it will be L alpha T minus delta, and the corresponding strain will also get reduced by the amount as delta L has got reduced. So it will be L alpha T minus delta divided by L, which we can compute as shown over here. Similarly, using the Hooke's law, we can calculate the corresponding stress being caused in this bar. Now let's look at one numerical and try to understand this in a better way. Now here we have a similar bar which is of the length 6 meter length and 2.5 centimeter diameter, and it is being contained between the two walls as shown over here. The initial temperature is given as 80 degrees Celsius, and from that the temperature get reduced to 22 degrees Celsius, so there is a decrease in temperature. So decrease in temperature will cause contraction in the bar, and because we are not allowing this contraction, there will be tensile stresses set up in this bar. So in this question we need to calculate the pull exerted by the rod or the bar on the walls. You have been given the numerical value of the thermal coefficient of expansion as 11 into 10 to the power minus 6 by degree Celsius, and the modulus of elasticity, which is perhaps steel, of the value 200 gigapascal. Now let's take the first case when walls are perfectly rigid and are not allowing any yielding. First we calculate the change in temperature, and that comes out to be 58 degrees centigrade, and let's calculate the corresponding strain that is being produced. So the corresponding strain will be the deformation divided by the original length, so L alpha T divided by L, which is nothing but alpha T. You substitute the value of alpha and change in temperature T and can calculate the strain. Using that we can find the corresponding stress value if we multiply the strain with the modulus of elasticity, which in this case is 200 into 10 to the power 3 in Newton per millimeter square values. Now we can calculate the pull or the tension in the bar using finding the area of this bar and multiplying it with the corresponding stress value. So as the 2.5 centimeter diameter is given, so we convert it into millimeter. This is already in Newton per millimeter square, and using this we can calculate the value of pull exerted by the bar as 62.64 kilonewton. In the second case, the wall has yielded by amount of 1.5 millimeter, so it is not perfectly rigid. There is a movement of the wall allowed by the amount 1.5 millimeter. So the actual deformation that has taken place in the bar because of the wall get reduced by the amount 1.5 millimeter. So we have L alpha T minus delta, that is being calculated as 2.328 millimeter. We can calculate the corresponding strain by dividing it by the original length of the bar. We can find the stress, and multiplying the stress with the area of cross section of the bar, we can calculate the value of pull that is being exerted, and now the new value will be 38.1 kilonewton. So you can see these are very simple questions, and using this method we can find the tension or the stress values or the strain value that is being produced in the bar because of the change in temperature. Now let's take another case. In this case we have the bar of a varying section, so it may be made up of the two section of the bar may be made up of two different materials even, so they may have different values of modulus of elasticity as well as different thermal coefficient of expansion. Their length and area in general may also be different, so A1 A2, L1 L2, similarly E1 E2, alpha 1 alpha 2 are the terms which you know. So as a result of increase in temperature, this bar ABC will tend to expand. If the temperature is increased, this will try to expand, and there are rigid walls at the end, they are not allowing it to expand, so they will set up the compressive stresses in this bar. The internal stresses that will be produced in this bar will be shared by both the portions, while the compressive force that is acting in this bar for each of these sections will be equal. So net compressive force that is acting in the section AB will be equal to section BC. So we can say the compressive force magnitude will be stress multiplied by area for the first bar equals to stress multiplied by the area of the second bar. So sigma 1 A1 will be equal to sigma 2 A2. Now the total change in the length which is suppressed due to the wall can be calculated by simply addition of the change in length of the first and the second section, where the individual value can be calculated using the thermal expansion coefficient as L1 alpha 1 T and L2 alpha 2 T, or we can calculate them using our mechanics of solids relation by multiplying the strain values with the length of the section. So strain is nothing but the stress divided by modulus of elasticity for that section. So sigma 1 by E1 into L1, and for the second one it will be sigma 2 by E2 into L2. So using these equations from 1 to 4, we can identify the value of strain, stress, and the load being applied in this sections. Now let's again go and see a numerical. Now in this case, the first section of the bar is made up of steel and the second section is made up of aluminium. So we are using subscript S for the steel and A for the aluminium. The area of cross section of both the sections are given to you as 1500 millimeter square. You know the value of materials. One is for steel is 200 gigapascal. For aluminium, the modulus of elasticity is 75 gigapascal. You have also been given the value of alpha S and alpha A. You can see that alpha A is far greater than alpha S, and both the values are available to you. You have also been given the change in temperature. So temperature is changing from 38 to 21 degrees Celsius, causing a fall in the temperature of the magnitude 17 degrees Celsius. Now let's take the first case when the supports are not yielding or there are the perfect rigid support, the walls are perfectly rigid. Now in this case, as I told you earlier, that there will be, because there is a reduction in the temperature, so the bar will be not allowing, the walls are not allowing the bars to contract, causing the tensile stresses to set up, and the tension force that will be in the steel and aluminum, they both will be equal in magnitude. So sigma SAS, which is the tension force in the steel part, will be equal to sigma A into AA, which is the tensile force in the part of aluminum. Let's substitute the value of areas here, and you can calculate a relation between sigma S and sigma A with the help of this equation. We can find the deformation in the individual section of the steel and aluminum part. As we know, the LS, the value of the length of the steel part, its expansion coefficient, and the change in temperature, and we find that this value turns out to be 0.119 millimeter. Similarly, you can do the calculation for the aluminum section. You will find that it is also coming out to be 0.119 millimeter. So the total deformation will be the sum of these two, and it will be 0.238 millimeter. Now let's use the Hooke's law part, and for the deformation we express it as the multiple of strain multiplied by the length. So this is strain in the steel part multiplied by the length of steel part, strain in the aluminum part multiplied by the length of the aluminum part. So it is also the sum of these will be equal to the delta L. So let's substitute the value of sigma S as 0.5 sigma A from here for the sigma S, and then we substitute the value of ES as 200 into 10 to the power 3 Newton per millimeter square. Length of steel bar section is 600 millimeter. Similarly, we can do the exercise for the aluminum part, and their net sum is equal to 0.238. From this equation, we can calculate the value of sigma A, which will come out to be 43.3 megapascal, and using this equation sigma s equal to 0.5 times sigma a, we can calculate the value of sigma steel as 21.65 megapascal. So this is our first case in which the supports are not yielding. In case the supports are yielding, suppose in the question you are given that the supports comes near to each other by a magnitude of 0.1 millimeter. So the total net deformation which was supposed to happen has got reduced by the same amount. So we subtract from 0.238 millimeter, which we have calculated over here, to this part. So it will come out to be 0.138 millimeter. So we equate 0.138, the total deformation, again with this formula which we have already calculated as 5.5 into 10 to the power minus 3 sigma a, and again calculate the value of sigma a and sigma s. Sigma s is simply half of the sigma a, and this time values will come out to be 25.1 and 12.55 megapascal respectively. Now let's take another case for the thermal stresses. Now this is a very interesting case because here we don't have any retaining wall. The stresses are not being produced because of the effect of some retaining walls. But here we have a case of a composite bar where the two different or the two dissimilar materials are joined together either by welding or by some kind of a temporary fastening process, such as, let's say, nut and bolt, or maybe using the rivets. So if you have two dissimilar materials, like let's say here we have given the example of steel and brass, they are joined together, they are welded together, then because of the change in temperature, the thermal stresses will set up in them. Why is it happening? Let's try to understand that. So we have a steel bar, we have a brass bar. So we can see the value of the steel geometric parameters, area and length, as well as the material property as E2 and E1, Young's modulus. We also know the value of thermal coefficient, expansion coefficient of the steel and brass, which are alpha 2 and alpha 1 respectively. We know that the brass has higher thermal expansion coefficient in comparison to steel, so alpha 1 is greater than alpha 2. So in the case if these two bars are not joined, they are free to expand independently, they are not fastened together by welding or let's say some kind of fastener. So they will, if there is a change in temperature, let's say there is an increase in temperature, they both will expand, and their expansion can be calculated using the formula of L alpha T. So for the brass it will be L1 alpha 1 into T. T is the change in temperature, and for the steel it will be L2 alpha 2 T, and they both will be both are shown here. We can see that here that the steel bar has expanded by this much amount, while our brass bar has expanded by this much amount. So this is the case when they both are free to expand. These two bars are not joined together. What will happen if we fasten them together, if we join them together by using some method of joining process, a temporary or permanent joining method? So if these two are together joined, so they are bound to have the same expansion because of the rise in temperature. So when the temperature is increased, the brass bar will try to increase in length, and steel bar will also try to increase, but as they have unequal expansion rate, so because of this the steel bar will be pulled and it will provide you more expansion than it would have provided if it was alone. Similarly, the brass bar was also expanding, but here it is contracted and providing you less expansion because the steel bar is trying to pull it down. So you see here, because these two pieces of different materials are joined together, so having different thermal expansion coefficient, so the one which is having higher thermal expansion coefficient will have compressive stresses being induced in it, while the one which is having lower thermal expansion coefficient will have tensile stresses being induced in them because of this. Now here I have written that as alpha 2 for brass is greater than alpha 1 of steel, after joining the bars, the brass will be in compression and steel will be in tension due to the thermal loading. But even being of the different nature of the compressive and tension, their values will be equal. So the same amount of compressive or tensile load will act in the brass and steel part. So that's why your sigma 1 A1 will be equal to sigma 2 A2. Now the epsilon is the actual strain which is happening in the composite bar in this case. So epsilon is the actual strain that is happening here. So in that case, the strain in brass bar can be given as alpha 1t minus epsilon, because alpha 1t would have been the deformation or the strain if there has been free expansion, but actual strain that has happened is epsilon. So the amount of strain, compressive strain that has been induced in the brass bar is of the magnitude alpha 1t minus epsilon. Similarly, the strain in steel is calculated by subtracting the value of alpha 2t from the actual strain value epsilon. We can sum these up two strains and calculate the value of epsilon 1 plus alpha epsilon 2 equals to t times of alpha 1 minus alpha 2. Here from the Hooke's law we know that epsilon 1 will be equal to sigma 1 by E1 and epsilon 2 will be equal to sigma 2 by E2. Now let's use these concepts that we have learned into a numerical, and we see here we have a very specific case in which a steel bar is sandwiched between two aluminum bars. So there are on outer side there are both two aluminum strips, and at the middle there is a steel bar. The length of this arrangement is of 200 millimeter. Their thicknesses are given also here. We can see that the 8 millimeter is the thickness of steel bar, while 6 millimeters are the thickness of the aluminum strips on both sides of the steel bar. The width of these bars are given as 20 millimeters. So this sandwich arrangement is joined together by some kind of a fastening method. Now there is a change in temperature of, let's say, magnitude 50 degrees Celsius. We need to calculate the amount of stresses that are being generated in steel and aluminum parts. Here we are given the value of aluminum and steel thermal expansion coefficient, and we see that alpha A is almost twice of the alpha S. We are also having the value of modulus of elasticity for both the materials, and as well as we can calculate the area of the steel bar and the area of the aluminum bars. So area will be, for the steel bar will be simply the width B, which is equal to 20 millimeter multiplied by the thickness 8 millimeter. So that will be 20 into 8, that equals to 160 millimeter square. For aluminum bar the area will be doubled, because for individual section it will be 20 into 6 millimeter for one strip. So 2 times of 20 into 6, that will be 240 millimeter square. Now because of this change in temperature, there will be stresses being produced, and the compressive stress that is being produced will be equal to the the compressive load that is being produced will be equal to tensile load. So that's why sigma SAS will be equal to sigma AAA, and we substitute the values of area here and calculate the relation between sigma S and sigma A from the equation 1. We can find the strain in steel bar using Hooke's law, that is stress divided by modulus of elasticity for steel. Similarly for aluminum rod, sigma A divided by 18 to 10 to the power 3. We have already computed a relation between the sum of the strain, so let's apply that, and for epsilon S and epsilon A we will substitute these values from here in these two parts. So after doing this, we'll get this equation 2, where we will put the value of sigma s from equation 1 here into the equation 2 and calculate the value of sigma a from the equation 2, which will come out to be 30 megapascal, and for sigma s it will be coming out to be 45 megapascal. Now there are a lot of numericals which are given in your books on thermal stresses. We have already done the compound bar cases. So I would suggest that you go through all those numericals, the solved as well as the unsolved numericals, and see that how you can understand this concept more better with the help of them.